Okay, let's start with this problem on photoelectric effect. So here the question is, radiation light is used to extract electrons from a photocathode. The stopping potential is 3 electron volt. What is the maximum speed of photoelectrons extracted? And if the wavelength is 200 nanometers, what will be the threshold frequency of the metal? Now let's remind what is the stopping potential. So we know that the stopping potential is the work that has to be provided, the electric work or the work of the electric force has to be provided to stop all electrons, which means the work will be equal to 1/2 mv, the maximum electrons of any, the maximum kinetic energy of any electron extracted by this photon. Okay, so we want to know Vmax. So we know that the stopping potential is 3 volt. So this means that the kinetic energy, which is equal to EV0, which is equal to the 3 electron volt. Okay, we can also convert it to joule. Okay, so now this kinetic energy is equal to 1/2 mv max squared, and we are looking for this maximum kinetic energy. Okay, so the maximum will be equal to 2k over m and the square root of everything, and then we can do the calculation. Of course, here we have to convert the kinetic energy to joule divided by the mass of the electron, which is 10 to the negative 31 kilogram, and you will get a speed of around 5.9 10 to the power 5 meters per second. Okay, now let's go to question B. So the question B is asking about if the wavelength of the incident photon is 200 nanometers, what is the threshold frequency? So what we know that the lambda is 200 nanometers. What will be the threshold frequency? Now, remember, the threshold frequency is the minimum frequency that we need to provide in such a way to produce only the electrons with kinetic energy. So what we can do here is HF minimum. We need, the first thing we need to do is to calculate this work function. Okay, so we know that HF, okay, is equal to phi plus the kinetic energy, which means the work function is equal to HF minus the kinetic energy. Now we are given the wavelength. This means the work function is equal to hc over lambda minus kinetic energy. So in general, we would like this to be an electron volt, and this one is also an electron volt. So we know that hc, the hc is of the order of 1240 electron volt nanometers. Okay, so this means that phi will be 240 electron volt per nanometer divided by 200, because this one is an electron volt nanometers. See, this one must be in nanometers, which will give us an electron volt unit minus 3 electron volt, because the kinetic energy is 3 electron volt. This will give us 3.2 electron volt as the stopping potential. Okay, so the stopping potential is 3.8 electron volt. Now we can calculate the minimum frequency. So H will be the stopping potential, which means that the minimum frequency will be equal to 3 electron volt, but then you have to convert to 10 to the minus 19 divided by 6.6 10 to the negative 34. Okay, and this will give us a frequency of doing the calculation, it's 0.78 10 to the power 15 hertz. Okay. So the second problem, we have a 300 keV photon that is incident on an electron and gets scattered. Of course, here we have a clear Compton scattering. Okay, so we have a photon that is scattered over an electron. So here I will call it HF. It has lambda, and this one will have an HF prime lambda prime, and the electron will be scattered with the momentum, kinetic energy, and then the angle of scattering, and the recoil angle of the electron is phi, and the scattering angle of the photon is theta. So the first question is, what is the wavelength of the incident photon? We know that the energy of the incident photon is equal to 300 keV, and we would like to calculate lambda. We know that HF, which is the energy, is equal to HC over lambda. But lambda equal to HC over E. Now, as I mentioned, we can keep this in electron volt, and this is 1240 electron volt nanometers divided by, and this must be in electron volt, 300,000 electron volt. This will give you lambda is 4.13 10 to the negative 12 meters. Okay, this is the first question. Second question, what is the Compton wavelength associated with the initial electron? The Compton wavelength is defined as the ratio of the Planck's constant to the momentum at rest of the electron. So the Compton wavelength, this is a quantity that we use in physics. It's equal to the Planck's constant divided by the rest mass of the electron. Again, here, what I can do, I can easily multiply by C here and multiply by C here. So the reason I'm doing this is to take benefit of the fact that this is electron volt nanometers. So here it will give me 2040 electron volt nanometers. But since this is in electron volt, this must be in electron volt. We know that the mass, the rest mass of the electron is 0.511 MeV, which is 10 to the power of 6. So it's 0.511 10 to the 6 electron volt. Okay, and we can calculate this value. Okay. The question C is, the photon is scattered with an angle of 37 degrees. Calculate the change on the in the wavelength. What is the change on the wavelength? Now, what is the meaning of the scattering angle? This means that theta is 37 degrees. Okay, so this angle, the scattering angle, is 37. What is the change in the wavelength? The change in the wavelength is given by this formula, which is the difference in the wavelength between the scattered and the incident is equal to mc 1 minus cosine theta. Okay, again, we can easily use the same thing, the hc over mc squared 1 minus cosine 37, and we can easily find that the change is 0.005 nanometers. Okay, and obviously, what is the question D? What is the wavelength of the scattered photon? Well, the wavelength of the scattered photon is lambda prime, and so lambda is lambda plus delta lambda, and this is delta lambda. So we know lambda, we know delta lambda, and the problem is solved. Okay, let's go to another problem here. Yeah, so here it's mostly about the pair annihilation and production process. So the first question is, in a pair annihilation process, an electron and positron at rest annihilate and produce two photons. It's very, very important to understand that this is at rest. So an electron and positron at rest will produce two photons. Okay, I will call them HF1 and HF2. Now prove that these two photons have equal energy. This is, so we have to prove that these two photons have equal energy to be calculated and are produced in opposite directions. Okay, right? Now, let's start by the conservation of momentum. Conservation of momentum, the initial state is this one, and the final state is this one. So the initial state, the momentum is 0 because the two electron positron, which is a positronium, is at 0. So the momentum, the conservation of momentum tells me that the momentum 0 is equal to the momentum of the first photon plus the momentum of the second photon, right? Well, this means that the momentum of the first photon is minus the momentum of the second photon. This means that in magnitude, the two momentums are equal. And we know that the momentum of a photon is h over lambda. So this means that in momentum, h over lambda 1 is equal to h over lambda 2. Lambda 1 and lambda 2 are respectively the wavelength of photon number 1, photon number 2. This gives me lambda 1 is equal lambda 2. And since the photon's energy is hc over lambda 1, then they are equal. The energies are equal. So E1, so HF1, the first thing is that HF1 is equal to HF2. Okay? And in addition to that, because the momentum is opposite direction, this means that they are produced with 180 degrees. Okay? Because they are equal, but in opposite direction. Now let's calculate HF1 and HF2. Conservation of energy. Conservation of energy, at the initial state, we have the electron plus the positron, which is 2 times the rest mass, the rest energy of the electron positron, because they are at rest. So the only energy they have is their rest energy. It is equal to HF1 plus HF2, which is 2 times HF, because the two photons have the same energy. So this means that each of the photon has the mass, the rest energy of the electron, which is 0.511 MeV. This is answering the first question. The second question, B, is in a pair production process. So the pair production is when you have a photon, HF, that produce now electron positron. Now, because of the conservation of energy, we have HF will produce the energy of the electron, which is the rest energy of the electron plus its kinetic energy, plus the energy of the positron plus its kinetic energy. I will call it K plus K minus. This is electron, this is positron. Now HF will be 2 times E0 plus K minus plus K plus. Now the minimum energy required is to produce the two rest energies. So this means that is to produce the electron and positron with kinetic energy equal to 0. So the photon must have at least 2 times E0, which means 2 times 0.511 MeV.